Very good morning to everyone. Welcome back to our lecture series on advanced hydraulics. So, you know we are in the module 4 on hydraulic jumps. I need not repeat the things again as what is meant by hydraulic jumps and all. It is a rapidly varying flow that occurs in the open channels. In the last class, we had discussed on the length of the hydraulic jumps. We have also discussed on how to measure the profile or how to create the profiles of hydraulic jumps, how to find the location of hydraulic jumps. This was also discussed based on various criteria. Suppose if y star is the sequential depth of the pre-jump depth, then if this post jump depth, if it is equal to the normal depth in the downstream, or if it is less than the normal depth, or if it is greater than the normal depth, how the jump location gets shifted. This was also discussed. We have also solved one example problem related to these aspects and all, right. So, today we will discuss how we can use hydraulic jumps as energy dissipators. So, you know that in hydraulic jump you have a supercritical flow that gets converted into subcritical flow. So, a supercritical flow means it comes with a high kinetic energy, that is supercritical flow is having higher velocity and it will be having more kinetic energy. So, this energy needs to be dissipated and the hydraulic jumps provides a provision to dissipate this high kinetic energy. So, generally for various hydraulic designs and hydraulic structures and all, you create hydraulic jumps so that the energy gets dissipated. So, what does the hydraulic jump do? How it dissipates the energy? That is, the incoming flow with higher velocity and outgoing flow from the jump with lower velocity, the kinetic energy is getting reduced. Now, in this aspect, the jumps not only dissipate energy, wherever jumps are provided, you will also be able to design the channel beds or the channel shoes in such a way that it gets protected. For example, if a supercritical flow is maintained for a longer reach, due to its higher velocity, there will be more scouring action on the beds here along these regions. To avoid that, if any provision for hydraulic jump is provided in that channel reach, then the velocity gets reduced and this velocity may not be able to scour the bed enough. It may not be having enough velocity to scour the bed. So, that way the channel beds are getting protected. So, for that purpose also hydraulic jumps are provided. Hydraulic jumps as an energy dissipator, if we use them, you require, means you actually say, if I just give a top view of a channel reach and if a flow is occurring from this left hand side to the right hand side, if a proper provision is given for a hydraulic jump within this reach, and if this is supercritical flow, subcritical flow, the channel beds can be appropriately rescued from the erosion cases and all. You require a certain reach, either the entire reach or the part of the reach of the channel, so that the hydraulic jump is being made within that reach, right. So, the part of that reach where proper provisions of hydraulic jumps are given, that is called stilling basin. So, a stilling basin, if I just draw the longitudinal profile this thing. So, it may be something like, say, a supercritical flow is coming like this and you are providing a provision in the channel bed such a way that from here the hydraulic jump is maintained or the hydraulic jump is created and the flow goes downstream. So, this particular reach of the channel, this is called stilling basin. Why? It is because it is a basin that provides the provision for hydraulic jump. Can you provide stilling basins? Means why it is called stilling basin? Because the beds of this stilling basin, they are designed with proper aprons and proper paved materials, such that erosion or scouring is prevented in those locations and all, and it can also sustain the high pressure created from the hydraulic jumps and all. So, that way proper designing means stilling basin is a particular location in the channel reach where the jumps are provided and all, like that we can design it. So, you can use stilling basins for dissipating energy. That will stilling basins will create hydraulic jumps that can dissipate the energy. Can you create entire reach as stilling basin? What do you think? Now, once you are in engineering field, you need to economize the thing. So, if you have this entire reach of the channel, say, and jump is like this, do you think that this particular length, if I provide the entire length as the stilling basin, will it suit the purpose? Now, this will be non-economical if the reach, if the length of the jump is too long. If it is a very long hydraulic jump, it will be quite difficult to provide the entire reach of that hydraulic jump as stilling basin. So, you need certain control measures. You need certain control measures to provide jump within the structure given. Okay. So, there are some control measures. So, it can resist covering, means the stilling basins, they are mainly used for providing hydraulic jumps, and that can resist covering, right. So, how to design the stilling basins and all. So, we are not going into the technical aspects of construction process in this thing. We are just giving a brief idea how to design the things. As we suggested, the entire length is non-economical. You can provide control mechanisms like chutes, sills in the channel bed or near the stilling basins, or you can even lower the level of stilling basin. See, if I just lower this portion like this, and if you give like this, so you will be having something like this. So, this will also, this stilling basin will also provide the jump, but it can be economical, right. So, that way we can design stilling basins according to the need, and also it should be in an economical way. So, for designing the stilling basins, one need to understand the jump position. So, for designing the stilling basins, one need to understand the jump position. We have studied in the last lecture how the location of the jump can be designed, means how you can infer the location of the jump based on the depth of flow in the upstream as well as downstream conditions. So, the jump position is quite essential for designing the stilling basin. You also require the tailwater depth and the conditions and the tailwater conditions. These are also quite essential. We will discuss them again. Also, the type of jump that is intended. The type of jump that is intended in that location. You have studied the types of jumps, right? For example, undular, oscillatory, steady, weak, steady, strong. Various types of jumps you have studied earlier. So, which type of jump is the thing that you are means you have an intention to provide at that location. So, that is also quite essential while designing the stilling basin. So, the jump position, we will deal with that first today. The jump position. So, jumps, it is formed, jumps are formed at the downstream of certain sources. Right. Jumps are formed at the downstream of certain sources. Some of the sources are like, say for example, overflow spillway. So, you can say suggest that there is an overflow spillway like this, spillway cross section, water overflows like this and reaches here, and here it just jumps. Okay. So, you can provide the stilling basin at this location, appropriate stilling basin. So, this is overflow spillway. You can also have hydraulic jump near sluice gates. Say if a sluice gate is provided in a channel, that means and if it is lowered, water just gushes out like this, and here a jump may be formed. Okay. So, sluice gates also provide hydraulic jumps. So, these things, how will you now design stilling basins, right? You need to and provide stilling basins where the jump is being suggested. We can suggest various cases now. Let us consider case 1. You have, as we are mentioning now earlier, let me just suggest that the various y1 is the pre-jump depth notations, y2 is the post jump depth, and let y2 dash be the tailwater depth. So, just going into the previous line, based on this tailwater depth, we can have various types of jump, means the jump location or the jump position will be varied. These things also you have studied, it is again I am just repeating it here. So, if you have this common notations, now for example, in the overflow spillway case, for the, as you know that we have approximated the channels as horizontal in many of the cases. So, please consider this as a horizontal channel. So, the overflow spillway is there, water is overflowing like this, it reaches here, and if this is your pre-jump depth y1, from here you have the depths. So, this is the channel apron, stilling basin and all. You let the tailwater depth be y2 dash. So, case 1 is if the post jump depth or the sequent depth, it is also sequent depth of y1. So, if y2 dash is same as y2, then this y2 dash and this y2 both are same, right. So, the jump will occur at that location wherever y1 is there, y1 wherever the depth of flow y1 has occurred or started, at this location itself the jump is formed and it will jump into the sequent depth y2. Okay. So, this is jump will form at y1 itself. There is no shifting of the jump. Okay. It is one of an ideal condition. So, if such a situation is there, what is the peculiarity? If such a situation is there, you can now easily suggest that you can design the stilling basin in this location, right. You know precisely the jump is going to occur here itself, because here the depth of flow is y1 as soon as it reaches becomes horizontal, and as soon as the depth y1 is reached, a jump is formed to its secant depth. So, you can appropriately design the stilling basin. There is no confusion in the situation. It is an ideal condition, but in nature rarely such ideal situations arise. So, you have to design, even if there is a marginal difference in the depth y1 or y2 or y2 dash, there can be shifting of the jump that may cause havoc either in the downstream or in the upstream conditions. So, you need to means although the case 1 is an ideal condition, it is rarely happen or it can be rarely envisaged in practical situations. So, what is the peculiarity here? In y2 is equal to y2 dash situation, you can readily use your, for the, as I am again reiterating here, we are using the rectangular channels. So, you can use the secant depth ratio relationship FR1 square to measure tailwater depth, or the tailwater depth is easily obtained from these things, from this particular secant depth ratio, and therefore, you can design it appropriately. Case 2. What is the case 2 suggesting? Suppose if the tailwater depth is less than the corresponding secant depth of the pre-jump depth y1, that is, let me draw the spillway. So, water overflows and reaches this depth. Okay, you are designing the stilling basin. So, in this case, when the depth y1 has reached, it is observed that the tailwater depth, this is the tailwater depth y2 dash. Okay. Tailwater depth is y2 dash. However, the sequent depth of the jump from this case is like this. See, it jumps into this position. So, this is y2. So, y2 dash is less than y2. Here is the tailwater depth. How the jump position, whether the jump's position will be at the same location, or it gets shifted, or it gets changed to some other form. How will you understand this thing now? Same thing I can just reiterate for the sluice gate also, if it is suggested. For the sluice gate also similar way, I can suggest. So, if this is the depth y 1, ideally it should rise to y 2, but however, it is found that the tail water depth is only y 2 dash. So, how the jump will occur? You have to design the stilling basin appropriately. So, in this case, what we have to suggest is that as y 2 is greater than y 2 greater than y 2 dash, that means the specific force at y 2, it is greater than y 2 dash, right. So, that cannot be happen, means it cannot occur like that. Therefore, your flow, it gets shifted, that is the pre-jump depth occurs like this, it gets shifted here. We have studied the particular profile and it reaches to a depth y 1 dash, where the sequent depth of y 1 dash is same as y 2 dash and the jump occurs like this. Okay. So, the jump is pushed downstream in this case, fine, the jump is pushed downstream. So, if the jumps are pushed like this, you know that you cannot appropriately design the thing. We do not know the length of the jump also, and also proper protection may not be there within these particular portions and all. So, it can cause erosion of the bed. If it is considerably pushed downstream like this, if it is considerably pushed, the entire bed can get eroded. So, you need to find where the location of jump occurs. So, using proper control measures and all, once again you can provide jump wherever the stilling basin is being designed, that is also quite possible. So, we have to avoid such jumps, that is wherever y 2 tailwater depth is less than the sequent depth, you have to avoid such depths, because such designs, it is not economical also. You cannot provide this entire reach as stilling basin, that will be too much costly. So, you have to think on such strategies where to design the stilling basin appropriately. So, you can avoid such situations. These situations can be avoided if possible. Next one is case 3. I have the tailwater depth greater than the sequent depth provided. So, again I am just drawing the same diagrams. This way I hope that by repeatedly taking the same things, it will just enforce in your mind the concepts in a better way. So, the depth of flow, it has reached y 1 here. Now, whether I need to provide stilling basin within this reach, say if this is the sequent depth y 2. However, it is observed that the tailwater depth is y 2 dash. Now, y 2 dash is greater than y 2. So, how the jump will occur, whether it will occur at this location. Now, you will see that depth y 1, this depth y 1, its sequent depth y 2, they are having same specific forces, but y 2 dash is more. So, it is having more specific force in that location. So, the pre-jump depth, needs to be shifted upstream like this. So, this jump will occur something, instead of occurring like this, it will occur something like this. Jump is shifted in the upstream direction, or it can also submerge, means jump is shifted upstream. the tailwater can also submerge. It can also submerge the jump. See, if this is getting shifted like this, you see that this entire portion is getting submerged, right. So, submerged jumps are also possible. So, submerged, for design purpose, one can suggest submerged jumps, because it is not at all creating any havoc. You have proper protective measures everywhere, and for the purpose of jump is also being suggested. But the drawback in submerged jumps are that it cannot dissipate, or it is not efficient in dissipating the energy. Whatever energy is coming in, almost similar energy may get transmitted. So, you cannot dissipate the energy that much in submerged jumps. Not efficient in energy dissipation. Fine. So, the next criteria which we have suggested is the tailwater conditions. About the jump location and all. There we assumed tailwater depth is constant. Earlier we assumed tailwater depth as constant. Based on that, we suggested see, this is tailwater depth y2 dash. So, you do not know whether the jump sequence depth of jump y2, y1. Based on that, we suggested the jump can move upstream or it can be pushed downstream and all. So, there in all cases tailwater depths were considered as constant. So, what I just like to ask, what happens if tailwater depth is not constant? What happens if your tailwater depth is not constant? It can happen, that is, the tailwater need not be constant always. Based on the discharge available, it can get fluctuated. So, if the tailwater depth is fluctuated or if it gets changed, you know that the location of the hydraulic jump gets shifted. Now, again the stilling basin wherever you have designed, it may not become appropriate. So, therefore, you require a certain analysis where the fluctuations of tailwater depth are also taken into account, right. See, for design purpose, as you might have studied in your hydrology courses and all, there are stage discharge curves or rating curves. A similar sort of thing, for design purpose, you require tailwater rating curves. What is this tailwater rating curves? You can have for the given location, wherever the stilling basin is designed and all, wherever the tailwater will be coming after that in the downstream of the source of the jump, wherever it is there, you can design for various discharges the corresponding tailwater depth. For this depth, for this much depth, for say for example, here if I just marked it, there could be a corresponding discharge. So, if I can plot q versus y2 dash curve based on various historical data and all, if you can plot them, if you can keep it ready for that particular structure there, then that can be readily used for the design purpose further. So, now I have a tailwater rating curve, This particular curve is called tailwater rating curve. If this is given there, one can easily now identify. Say for example, I have at a particular time I have a depth here, some value here. The corresponding discharge can be easily identified here, right. If I have another depth of tailwater at this location at another time, some other time, you can easily suggest that the discharge in that location is at this, the magnitude of discharge is at this corresponding there, right, that it can be suggested. So, using this tailwater rating curve you can use for design purpose. A similar type of rating curve you need to employ for jumps also. Rating curves for jumps. So, for jumps it is the post jump depth that we are taking into consideration, and if you can plot q versus the post jump depth, if you can plot it like this, this is now called jump rating curve. Okay. So, if you have these jump rating curves and the tailwater rating curves, you can easily use it for design purposes. So, we now you do not know, say for this particular channel reach you have only the fixed pre jump depth. So, this is the post jump depth y 2, your y 2 dash it can be greater than y 2 or it can be less than y 2. Okay. So, we have to suggest the suitable, we have to suggest suitable jump location as well as jump depths, right. So, that is the requirement for designing this stilling basin. So, we can have discussions with several cases. Case 1. Now, case 1 corresponds to, again if I plot the discharge rating curve, that is discharge rating curve with respect to tailwater as well as the post jump depth. Now, in this case, if the rating curves, if the tailwater rating curve as well as the jump rating curve JRC and TRC, if they are same, what does this imply? That is, if jump rating curve is same as the tailwater rating curve, this implies that y 2, that is the jump depth, and the tailwater depth y 2 dash both are same every time, right. That is the meaning. So, irrespective of the situation, that is irrespective, say if I am taking this depth, then the corresponding means discharge is here. So, if again if I take another discharge q 2, its corresponding depth, this thing, that will be having same sequence, that is the sequence depth as well as the tailwater depth will be same. So, irrespective of the discharge, jump will be provided. So, you know that in the source of the jump, that the pre jump depth it is a fixed value, that is say from the overflow spillway and all y 1 depth y 1, it is a specific quantity, means it is a specific depth. So, therefore, whatever type of discharge is coming from the spillway, now if y 1 is less, still there will be some discharge in the channel, right. So, if the discharge is getting reduced, it does not matter, the jump will be provided at the same location. So, jump will be provided at the same location. Again, this is an ideal situation which is not encountered practically, right. In practical cases, it is difficult to attain such ideal conditions and all. So, therefore, you need to design it for a more practical cases and all. You may not have the jump rating curve and tail water rating curve same every time, right. So, they are very rare. I can have the rating curve such that the jump rating curve is greater than the tail water rating curve. Fine. If I have such a rating curve, here the jump rating curve greater than tail water rating curve. That means, the y 2 depth of y 2 is greater than the tail water depth always. So, whatever discharge is there in the channel, the jump depth is always greater than y 2 dash. So, what does this create? What does this will create? It will always push. For such cases, it will always push the jump downstream. We have seen that when the jump depth is greater than the tail water depth, the jump is pushed downstream, right. So, you can use control measures appropriately to provide jumps in such situations and all. We can have another case. With respect to the jump water depth and tail water depth, if the tail water depth is like this and the jump water rating curve is like this. Here the tail water rating curve is greater than the jump rating curve. Therefore, y 2 is always less than y 2 dash in this situation. So, possible always there is chance of possible submersion of the jump, that is jump is shifted upstream. So, possible submersion of jump can also encounter in such situations. By providing proper sloping aprons and all, you can have effective jumps in this situation. We have seen that such jumps are not efficient, it cannot dissipate energy. If you want to design stilling basins for energy dissipation, then such jumps cannot dissipate that much energy, but by providing proper aprons and sloping aprons and all in the upstream location, you can have a better jump. Next case, we can suggest based on the rating curves is, if you have a jump rating curve like this and if you have a tail water rating curve like this, such curves it suggests that for lower discharge you have for lower discharges you have y 2 greater than y 2 dash, then in that situation the jump is moved downstream. For higher discharges you have y 2 less than y 2 dash, then you can have submerged jumps. Fine. So, you can design it appropriately. Next case is where the jump discharge curve is like this and your tail water discharge rating curve is in the following form. So, y 2 and y 2 dash. In this case, for lower discharge you have y 2 less than y 2 dash. For higher discharges, you have y 2 greater than y 2 dash. So, you can know where the submerged jumps can occur or where it can be used. Okay. So, these things stilling, if by providing proper stilling pools in these cases and all, you can have higher tailwater depth also for lower discharges, that can ensure a better jumps. Fine. Now, as for designing the stilling basins, you need to suggest the types of jumps, whether it is oscillatory, whether it is weak, whether it is undular, whether it is steady or strong, whichever type of jump is there, that you need to provide it beforehand itself. So, this usually in designs, jumps in the range 2.5 less than F R 1 less than 4.5, they are oscillatory jumps, right. It is better to avoid oscillatory jumps in design purposes, because oscillatory jumps, it is always having some oscillations and all, it is not at all steady, you will not get a steady flow situations in those cases and all. So, it is better to avoid oscillating jumps. Also, you need to understand that the tailwater depth, in last two cases also we have suggested, tailwater depth is quite essential, that is your jump depends on the tailwater depth. So, that is also quite significant, what type of tailwater depth, how much amount of tailwater depth you are providing. Based on that, the type of jumps will also get varied. For strong jumps like having fluid number greater than 10, in such jumps energy dissipation is less. Means if you want hydraulic jump for dissipating energy, then for higher fluid numbers it is not appropriate, means by providing stilling basin and all. So, you need to take that into account. Now, we will just briefly discuss on jumps in sloping channels. So, earlier our jump analysis, hydraulic jumps, we assume the channel bed to be horizontal, right. And based on that, in horizontal channels, whenever we consider, say, if the bed is horizontal, you have jump and all. The portion of hydraulic jump, whatever portion we were taking into account, and there the effect of weight was neglected. That is, weight in the, if the weight of the liquid in the hydraulic jump it is in the vertical direction, then whatever component of weight in the flow direction, they were neglected earlier. Now, in sloping channels that will not be possible. How the jumps are formed in sloping channels, or why? You know that in sloping channels, especially if it is a supercritical flow, how the jump will be formed? If there is any change in the bed slope in the downstream, say whether it becomes horizontal or whether it becomes adverse, whatever be, due to this change in slope, hydraulic jumps may be formed. So, we have to understand what type in what way it can be obtained. So, that is, change in bed slope will cause hydraulic jumps in sloping channels. I hope you recall in our earlier lecture also, we have suggested that suppose if a steep slope channel merges with a mild slope channel, or if it merges with a horizontal slope channel, then there is a high possibility of formation of a jump, and we do not know at which location the jump can be formed if the flow normal depths in both the locations are like this, right. So, we have to identify them. So, depending upon the depth and velocity, that is what is the depth, what is the velocity in the upstream condition, and also on the tailwater condition, we can identify at which location the hydraulic jump will form in the sloping channels. So, let me start it like this. So, the jump, if a flow in the steep channel, this is steep channel, or a sloping channel, let me suggest now, earlier we took it as a horizontal channel, right. The sloping channel, if it comes and merges with a horizontal channel, so there are three distinct possibilities. So, either the jump can form completely in the steep channel or in the sloping channel, or the jump can form in the interface somewhere here, or it can form completely in the downstream channel, which is the means. So, I can just again redo it. I will just for your this thing say if jump can form, in this case the jump is formed completely in the upstream channel, in the sloping channel itself. Another case is the jump is encountered in both the steep in the sloping channel as well as in the horizontal channel. In both the locations, the jump positions are coming into picture. Another case is you have the jump like this, and this is completely pushed to the downstream. The jump is completely pushed to the downstream. So, like that three situations one can assume for jumps in slope channels. So, what is the difference? Difference in jumps for the horizontal, and how do you analyze it in a different way for horizontal and sloping channels? So, as we suggested earlier, in horizontal channels you neglect the, say again I am just redrawing them, a jump is there and there is the horizontal channel, and if you take the control volume for the hydraulic jump, so you take these depths, this is the pre-jump depth and this is the post-jump depth y1, y2, right. And in this thing the effect of weight is neglected. However, in the sloping channel that may not be quite possible, that may not be quite feasible. You will see that the water is flowing and there is a hydraulic jump. If you take the control volume here enclosing the hydraulic jump, definitely the weight of water will be in the vertical direction, but due to a considerable slope, say if this is having an angle theta, the bed slope is having an angle theta, bed is having an angle theta with the horizontal, then there is definitely a component of weight in the direction of flow. So, that will also aid for the flow and you cannot neglect that component. So, we need to incorporate those also into account when we do the analysis for sloping channels. So, we can suggest that let us assume jump as a free jump. That is, in our earlier lecture we suggested that tailwater conditions can affect the jump location, and so we are assuming that the tailwater depth is free, that is whatever jump depth is occurring, that will be the depth in the downstream depth. So, if we have a free jump, so if I draw the control section, for the jump. Then let this be the depth d1, let this be the depth d2. Okay. So, you have the weight of water W acting like this. So, in this control volume, we can have we can incorporate the momentum transport equation. If you recall the momentum transport, then using the Reynolds transport theorem, I am just again writing it for your benefit. This is the volumetric integral. This is nothing but the time derivative, the volumetric integral v rho du plus the areal integral v rho v dot n dA. This we have done it earlier also, right. So, that is, it is suggesting the rate of change of momentum in the control volume. This is nothing but equal to the rate of change of momentum stored inside this volume plus the net outflux of the momentum across the control surfaces. Now, we have two main control surfaces, this on the left and on the right. All other control surfaces are not allowing the momentum, as this is predominantly a one dimensional case. We will continue with this portion now in the next lecture. We will have a brief quiz. So, first question. So, as we have studied today's this thing, based on the fixed tail water depth conditions, enumerate different cases of jump positions in a stilling basin. And the second question you are having is, why the weight of water in hydraulic jump is neglected in horizontal channels and it is significant in sloping channels. So, you can quickly answer the questions and submit the paper.